Okay, so just for the last part of this video, I wanted to refer to the video that I asked you to watch in week 1 of the course activities on the website, which was that video about friezes in architecture, which I claim is related to group theory. So one of the things that people study in group theory are symmetries of geometric objects. And that's something that maybe was not at all clear from the summary earlier about what abstract algebra is about. So don't worry too much about the connection there for the moment. We'll come back to it many times as the course proceeds. But what the video was about was symmetries of basically rows of tiles, rows of repeated tiles. And one of the things that group theory can do is classify kind of possible structures of symmetry. So the assertion in that video was that there are essentially 7 different types of examples of the sorts of symmetries that a frieze can have. And remember, a frieze, the word comes from design and architecture. It's basically a row of repeated tiles that all look the same. And in mathematics, we think of it as being an infinite row. So the picture here has 4 friezes, all with blank tiles, and the dots are supposed to indicate that these patterns continue indefinitely, both to the left and to the right. Okay, and so we're interested in the symmetries of these things. So symmetries, we'll come to precise definitions of all this stuff later, but we mean, are there ways of moving the entire frieze around so that it looks the same after the move as it did beforehand? So if all the tiles are identical, we can, of course, have translational symmetries, which just shift the entire picture a step to the right or to the left, or more than one step to the right or to the left. And all friezes have the translational symmetries. All of these at the moment are just rows of blank tiles with no decorations at all on them. So they also all have, for example, rotational symmetries. You could pick up the entire first line, rotate it through 180 degrees, and it would look the same as it does now. It has reflections. You could reflect it in the horizontal axis down through its center, so like this. And if you just do a sort of reflection in that line, the picture will look the same after as it did before. And they also have reflections in vertical axes. So question basically is, for different friezes, different patterns of tiles, how many essentially different patterns of symmetry can you have? Okay, and the first example in the video was an example that had translational symmetries only. So the little exercise for us here is to decorate these tiles so that they all look the same, and so that basically the overall frieze after we do it will preserve only the translational symmetries. So a way to do that, we have to make the tiles all look the same. So let's just, for example, do this. Put a little red sort of L like that down in the lower right of every tile. So it's supposed to be in the same position in each of the tiles. And we're supposed to now imagine a row of tiles like this that each has this little decoration in the lower right corner. Now, these tiles still all look the same, so the entire frieze still has all the translational symmetries. But it doesn't now have any rotational symmetries, because rotating through 180 degrees would turn this L into an L that would have the corner up in the top left. We don't have any of those in our picture. Reflecting in a horizontal axis would turn that L into an L that would look like this, but they don't appear in our picture. Similarly, reflected in a vertical axis would turn that L into a different looking L. So this frieze, as it now looks, only has translational symmetries and doesn't have any other symmetries. And as such, it sort of, in some way, is of the same type as the first example that was in that video. Okay, the second example in the video had translations. They all have translations because all the tiles have to look the same in all cases. Second one has translations and rotations through 180 degrees and nothing else. So again, we can think about how we might want to decorate our tiles so that we preserve rotational symmetry to 180 degrees, but not anything else. One way to do it, and certainly not the only way, is to do a kind of a diagonal stripe on each tile like this. Okay, so there's a frieze. It's different from the first one. Assertion is it has different symmetries from the first one, as well as looking different at a glance, which it also does. This frieze certainly has no reflections in a horizontal or a vertical axis, because if you reflect this diagonal stripe in a horizontal or a vertical axis, you get a diagonal stripe that goes the other way, and none of those appear in the picture. So this stripe still has the rotational, so it still has the translational symmetries. We can still step it along the line. Now it also has rotations through 180 degrees about any point which is the center of a tile. So any of these points and also about any point which is the center of the line that separates 2 points. So all of those green points are rotation centers for symmetry of this particular frieze. Okay, the third type of frieze group that was presented in the video was one that had translations and horizontal reflections only. And no rotations or vertical reflections. Translations and horizontal reflections. So here we've got to produce a picture where the decoration on each tile is something that is preserved under reflection in that blue line which goes along the center of all the tiles parallel to the direction of the frieze itself. And again, the blue line is not part of the picture of the frieze here. It's just to indicate the axis of horizontal reflection. So a way of doing that, for example, would be to put a sort of a V shape on each tile. That V shape sort of points to the right, so it's definitely not preserved under any reflection in any vertical line or under rotation through 180 degrees. So this frieze, which consists of that V repeated, has a horizontal reflection, but it doesn't have any vertical reflections and it doesn't have any rotational symmetries. And of course, it has the translation that we will always have. The fourth example in the video was one that had translations and vertical reflections only. So that means it must have vertical axes of symmetry, that if we reflect the entire frieze in these vertical axes, it'll have to be exactly preserved. So that means the vertical axis of symmetry, because it has to preserve the outline of the tiles regardless of their patterns. It has to like take a tile to a tile. So a reflection of that type can only go either through the center of a tile, the vertical line through the center, or through the vertical line between adjacent tiles. And you can figure out for yourself that if we have a frieze which consists of identical tiles and which has reflections in vertical lines of this type down through the center of the tiles, it'll also have them in the other vertical lines, provided all the tiles are identical. So a way of doing this, again, we can fill in some pattern whatever way we want to. It has to be preserved under reflection in those vertical lines and not under reflection in any horizontal lines or by 180 degree rotations. So again, we can use a sort of V-type pattern. For example, this is not the only thing you can do. And it should be, it has all those vertical axes of symmetry. It also has the translations, of course, and it doesn't have any horizontal axes of reflectional symmetry, and it doesn't have any axes of rotation, any points of rotational symmetry either, because if you rotate this V through 180 degrees, you don't get a shape that looks the same. So those are examples that correspond to the first 4 examples in the video that don't look the same as them, but from the group theorist's point of view, they represent the same structure of symmetry. There's 3 more to look at in the next slide. Okay, the 5th example of a frieze group that we're looking at has translations, horizontal and vertical reflections, and also 180 degree rotations. So if we try to draw a picture that has all of these symmetries, what we might notice is that the requirement of having symmetries in the horizontal axis and also in any vertical axis is going to mean that we're automatically going to get 180 degree rotations around the point where any 2 such axes intersect, because the composition of the vertical and horizontal reflections will always give us a rotation. So let's just see what can we do to achieve this pattern. If we go back to the first example, let's say that we want our tile to have a little decoration in a corner like that. If it's got reflections in the horizontal axis, it also has to have such a decoration there, and that'll have to occur in all the tiles. And if it's also going to have reflections in the vertical axes, or indeed 180 degree rotations, it's going to have the corresponding decorations also in the other 2 corners. So something like this would be an example of a frieze whose symmetries include both horizontal and vertical reflections and 180 degree rotations. In this case, the centers of the 180 degree rotations into the centers of all the tiles and the centers of the lines separating them. Of course, in fact, in this particular example, we could have got away without doing anything at all, because the symmetry group of the tiling of blank tiles that we started with is in fact exactly this one, this frieze group, which has horizontal and vertical reflections and 180-degree rotation. So in some way, it's kind of almost the simplest of all the friezes, even though it has a lot of symmetry. Okay, the next example is an interesting one. The next example was one which had vertical reflections and rotations only. Vertical reflections and 180-degree rotations only. Okay, and this is an example of a system of symmetries that's easiest to achieve when the tiles are actually not all identical but alternate in pairs. And if you look at the example, the sixth example in the video of the tiled houses, you'll see that in that particular example, the sixth one, which is the one with this particular frieze group, the tiles weren't all the same. They alternated between two types, and every second one was different. So here is a way of achieving such a frieze group. And let's stick to these examples of the little corner decorations again. So if we say that we'll have a corner here, and let's say that we want this center point of that tile to be a center for rotational symmetry, then we'd have to have another corner up here. We don't want to have a horizontal reflection, so it means the other two corners of that tile must not have these little decorations in them. So the vertical reflections, the axes of vertical reflections go between the tiles, and we have another one. The next tile is the image of the previous one under this reflection in that vertical line, and it has its decorations in these sort of opposite corners to the previous one. Again, that's an axis, a point of rotational, center of rotational symmetry to 180 degrees for the entire pattern. And the tiles just alternate. Every second one has its two decorations, either in the top right and lower left corners or in the upper left and lower right. So here we're in the upper left and lower right, and so on. And that's how the frieze looks. So in this particular case, all of the vertical lines between adjacent tiles are lines of vertical reflection symmetry. We don't have horizontal. We don't have a reflection in the horizontal axis is not a symmetry, but we might notice, and also the other comment is that the basic repeating unit in this particular example is two tiles. So this is the repeating unit, it consists of two tiles. So the translational symmetries, the smallest one involves two steps instead of one, moving each tile to the position that the next one is not a symmetry, but moving each tile two steps to the right or left is a symmetry. So in this particular instance, it's different from the other examples. The basic repeating unit is two tiles as we've drawn them. The translational symmetries are sort of steps of length 2 along the length of the frieze. There are reflections in all the vertical lines between adjacent tiles. There are rotations about the point, which is the center of each tile. And there are no reflections, there are no reflections in the horizontal axis, but there are what they call glide reflections. So if you notice, if you flip this whole pattern in the horizontal axis, you don't preserve it because you adjust the positions of the corners. But if you flip it and then take one step to the right or left instead of two, then you achieve a symmetry. So this one, in fact, has glide reflections as well as the reflections in the horizontal and vertical axes and the 180-degree rotations. And then the last example, which was number 7 in that video that we looked at, is the one that has rotations and glide reflections only. So remember what a glide reflection is. A glide reflection is a symmetry which is achieved by reflecting in the horizontal axis and also translating some distance. Okay, so for a true glide reflection, the translational step won't be a translational symmetry of the overall pattern. So what we're going to do, what we're going to produce is something where horizontal reflection is not a symmetry of the whole frieze, but if you do a horizontal reflection and then do a translation of just half the length of the tile instead of the full length, we will get a symmetry, and that's our glide reflection. So in this case, if we just draw the horizontal axis of reflection, so again, this is not supposed to be really part of the picture of the frieze. It's just this blue dotted line. It's just to mark the horizontal axis to the center of all the tiles. And we're going to construct a pattern, a frieze pattern, which has glide reflections, but not reflections in a horizontal axis, no reflections in vertical axes, and no rotational symmetries. So if we put a kind of a diagonal line like this in the sort of lower left quarter of our square tile, okay, if we reflect that on the horizontal axis, we'd get a diagonal line going the other way. We don't want to have reflection in the horizontal axis as a symmetry, but if we take the mirror image of this diagonal in the horizontal axis and then just translate it to the right by half a tile, then we get a line like that in the upper right. Do the same for each of these tiles, and we see we've got a frieze. All these tiles are identical. There are no rotational symmetries. There are no reflections, but there's a glide reflection. There's a symmetry which consists of reflecting in the horizontal axis and then stepping to the left or right, not by the full length of a tile, but by half of the length of a tile. Okay, so that brings us to our first video challenge. And the challenge for you from this video is to create your own picture of 7 frieze diagrams that have the 7 different symmetry structures, just as we did during that video. So make them look as different as you can from mine. Here, I'm not asking for any high-tech solutions. A photograph of a handwritten piece of paper is fine, but it would be nice if we get a range of responses showing how different friezes with the same basic groups of symmetry can look. And again, don't worry if you didn't sort of follow every detail of what was going on in that lecture. You should kind of get the basic idea of what the different symmetry types are. That having to go at creating your own examples of friezes, I think, should be hopefully an accessible task. So have a go at it. You're welcome to send me just a photograph as a JPG file if you want to. During this week's workshops, we will talk about how to convert it into a sort of slide with an embedded image. So thanks very much, everybody. Thanks for watching, and see you soon. Good luck. Bye-bye.